Hi everyone, I'm Professor Wasim Jabi, and in this tutorial we're going to cover some of the more advanced methods to create topologies and geometries in topologicpy. If you have seen the previous tutorial, you will know that in order to show anything in the environment that I'm using, which is Jupyter Lab, I always have to specify a renderer called Jupyter Lab, and that can become tedious to type it all the time. So what I'm going to do in this tutorial is to define a function called show, lowercase show, where I will give it a topology and it will automatically use topology.show and use the same topology and specify the renderer to be Jupyter Lab, as you can see here on the screen in that definition of a function called show. So let's go ahead and execute that function. We'll put it at the top right after we have imported all the libraries. And now let's test it out to make sure it's working well. So I'm going to make a simple prism. So C is equal to cell.prism. And then, unlike the previous tutorial when I said topology.show C, renderer equals Jupyter Lab, I'm just going to say show C. So it's much shorter and faster to type in. And let's see if that will work. And there it is. So it works really well. So we can start using it going forward. Okay, so the first thing we're going to do is kind of look at some of the 2D methods for creating more sophisticated geometry. One of them is to offset a wire or offset a face in order to create a boundary. This is not the same as scaling a face or scaling a wire. It simply takes every edge of the original topology and offsets it and then miters it correctly in order to create the new geometry. And then it combines it with the other one. And you can imagine, for example, if I take a rectangle and I offset it, the result will be almost like a ribbon with a hole in the middle. So let's try some of these things. Okay, so let's start with one of the simpler ones in 2D, which is to create an offset from a wire. So basically an offset is not like a scale. It basically takes every edge in the topology and displaces it or offsets it by the desired amount, and then connects the edges correctly and miters them correctly. So that could really work well for more complex shapes, let's say with concave and convex shapes or edges. So let's go ahead and exercise that. So first I'm going to create a 1x1 wire. So W is equal to wire.rectangle. And then let's create the offset. So the offset is wire.offset. And I give it the original wire and an offset amount. Since the wire is 1x1, I'm going to give it an offset of 0.2. The default for positive offsets, if you say 0.2 instead of negative 0.2, is that it offsets to the inside of the original wire. So offset is equal to 0.2. And let's go ahead and show both of them. So we can say show, we can make a list out of them and send them to the show function as we have defined before. So we're going to show the original wire, which is called W, and the offsetted wire, which is called offset. And now we don't have to write the renderer method or the parameter. Oh, sorry about that. Sorry, it is, I made a mistake here. It's not offset, it is by offset. And here it is. That is the wire and the offset, and the smaller rectangle that you see here is the offsetted wire. Now, if you apply that to a face, so let's repeat the same method, but with using a face. So F is equal to face.rectangle. And then offset is equal to face by offset. And then the offset is again 0.2. And let's show the offset by itself. I believe it's the whole face, but we can check that. Oh, sorry about that. by offset requires the original face, so I forgot the F here for face. So you give it the face and then you give it the offset. So that is the actual offset, not the actual thing. So let's go ahead and draw both of them. And now that is an offsetted face. Obviously, what you can do is you can take the wires of those and you can make a face which is called by external boundary and internal boundaries being holes, and you can get the face out of that. So let me show you that based on the original wire and show you how to create a face that has a hole in it. So now that we have here, going back to this cell, now that we have a wire and an offset, we can create a new face, which is face dot by wires, and we can give it W as the external wire, and then a list of internal wires or internal boundaries, which are considered to be holes, and we can make a square bracket and say we only have the offset as an internal boundary. So face dot by wires W for the external boundary, and the list of internal boundaries, in this case we only have one. And instead of showing the wire and the offset, let's go ahead and show F, and let's take a look at what that looks like. So not this one, but this one. And as you can see here, there's a hole in the middle, and you have what looks like a ribbon. Great. So now moving on, let's go ahead and look at two very classic ways of creating a segmented face. One is called Voronoi, and one, of course, and the dual of that, or the alternative to that, is called Delaunay triangulation. So if you are not familiar with those are obviously very popular. They have been popular for a long time in our area. But let me show you the Wikipedia page on each of them so that you know what they look like. So this is the Voronoi diagram, in which you specify a series of points within a face, and it segments that face into regions where every point in that region is closest to the point that is specified by that region. And that's really good for spatial segmentation. For example, if you need to find out where to put bus stops and what areas they need to cover, you can create a Voronoi analysis of your region, and you can find out what is the most efficient way to distribute those locations. The Delaunay, on the other hand, is a triangulation method, and it is basically what is called the dual graph, kind of the alternative to a Voronoi diagram, and you can read more about it right here. So let's go ahead and try to create a Voronoi and a Delaunay. And because these create a shell, you will find them under the shell class. So let's go ahead and consult the API documentation, look to shell, and if we go down to V, you see Voronoi here, and it requires a list of vertices and a face that will be segmented by those vertices. And since we are here, let's take a look at the Delaunay, and that is under D, and there it is. Again, it takes a list of vertices and a face that will be segmented by that, or triangulated by those vertices. So let's go ahead and try to implement that. So here, first of all, we're going to create a series of vertices, and I'm going to place them in a face that is 1 by 1. So let's first of all create that face. So face is equal to face.rectangle. And then let's create perhaps 3 vertices. So V1 is equal to vertex by coordinates, and we'll give, let's say, minus 0.1, minus 0.2, and 0, making sure that those coordinates happen to be inside the face, which is, as you know, it is 1 by 1, but it's centered on the origin. Therefore, its range is from minus 0.5 to 0.5, and minus 0.5 in the y to 0.5 in the y. So any numbers that in that range will happen to fall within the face, and we can use them to segment the face. Experiment with different numbers as you see fit. I'm going to add only 3 for now, but you can add as many as you would like. So in the next one, I'm gonna try vertex by coordinates, maybe 0.15, 0.25, and 0. And the third one, by coordinates, let's say perhaps minus 0.33, 0.33, and 0. Great. And let's make a list out of those vertices. So I'm going to call that list vertices, and it's equal to square bracket v1, comma v2, comma v3, square bracket. So that is a list of vertices. So let's go ahead and create a Voronoi first. I'm going to call it Voronoi is equal to shell dot Voronoi. And the first argument is the list of vertices. That's called vertices here. And then the second parameter or argument is called is the face, so that's called f. And let's show Voronoi and see what we get. If we don't like how it looks, we can change the coordinates of the points. Here it is. Those are only 3 points, so very, very simple. Great. So now let's go ahead and use the same vertices and to create a Delaunay. So basically, we can just use them as they are. So I'm going to call it Delaunay is equal to shell dot Delaunay. And excuse me if I'm not pronouncing it right. I actually do not know how it's pronounced, but I call it Delaunay. And then same thing, a list of vertices is called vertices, and the face is called f. And let's show Delaunay. And this is the Delaunay triangulation. Now, to see how this Delaunay triangulation corresponds to the Voronoi, let's draw them together and see how they overlap. So show, and let's make a list out of the Voronoi and the Delaunay. So we put them in a square bracket, and let's see what that looks like. And there they are. One is the Voronoi segmentation, and the other one is the Delaunay triangulation. Okay, another couple of geometries that you can create that are a bit more sophisticated, let's say, than a rectangle or a circle, are found in the shell class, and they are called hyperboloid, rectangular domain, and circular domain. So let's take a look at the API to see how these are created. So let's go to the shell module again and look under H. So this one is called a hyperbolic, paraboloid, circular domain, and there is one called hyperbolic, paraboloid, rectangular domain. Unfortunately, these names are very long. Obviously, if you're using something like topologicpy inside Grasshopper or SpurChalk or Dynamo, you don't have to type the names. You can just simply connect the boxes. But if you're using it in a scripting environment like JupyterLab, unfortunately, you will have to type it. So instead of me making a spelling mistake here, I'm just going to take all of this name here and copy it and then use it in my scripts. So let's go ahead and try that. And I'm going to call it H, and it's going to be shell dot, and then I'm going to paste that long name, hyperbolic, paraboloid, rectangular domain. Now the difference between rectangular domain and circular domain, as you will see in the result, one will look like if you look at the footprint of it, it will be a rectangle that has been lofted, and the other one will have a footprint of a circle. So first of all, I'm not going to do any inputs. I'll leave that to you to experiment with and change the numbers in order to get different results. So let's look at the result of this one, topology.show H, and the renderer is JupyterLab. And there it is. And you can change, it's a saddle shape. You can change the apex heights and the lower part height as well. And let's go ahead and change it to a circular domain. So I'm just going to change the word rectangular to circular. And take a look at the result there. And there it is. As you can imagine, it looks like a saddle. And now we're going to cover some additional ways of creating more sophisticated geometry. Another way or another interesting shape to create is a roof, which is obviously very relevant for architects. The roof method in topologicpy takes a base shape, like almost like the footprint of the roof as a face, and then takes an angle, which is the angle of inclination for the roof that you would like, and then creates a cell out of that. There are alternatives to the cell.roof. You can create, for example, a shell.roof, which only creates the inclined surfaces, but not the bottom surface. Therefore, it is a shell and it is open. And there is also a 2D version of that called wire.skeleton that creates the footprint of the roof. So please explore these. But in this tutorial, I'm going to show you how to create a roof cell, which is an enclosed volume. Now we need a base face. Now an interesting footprint to use is perhaps a star. So let's go ahead and create a star. So let me go here and place my cursor. So F is equal to face.star, and then the number of rays are going to be 5. So I'm going to create a pentagonal star, and then I'm going to create the roof. So I'm going to call that roof is equal to cell.roof, and it requires a footprint. As I said, that's the F, and then it requires an angle of inclination. So the angle is, let's say, 40 degrees, and let's display the result. So topology.show a roof, or if you have created a function that kind of reduces the amount of typing, you can just simply use show roof. Renderer equals Jupyter Lab, and let's take a look at the result. And here it is. As you can see, a very clean topology. This is an enclosed shape that you can use. And obviously, some more complicated footprints might cause you problems with the roof algorithm, but for the most part, it works really well. Another way to create three-dimensional geometry from two-dimensional profiles is to use a thickening process, basically a lofting process. In topologicpy, this is a method called cell.byThickened face. So let's go ahead and try that. First, we need a face. So F is equal to, we're going to create a star shape as a face. So face.star. And let's specify the number of rays, for example, to be 5. And now let's go ahead and loft that up and create a thickened cell. So C is equal to cell.byThickened face. So just make sure you spell it correctly. And we give it the face, and we give it the thickness. So let me check, first of all, what the parameter is called. So let's go ahead to cell here and look at byThickened face. And the input parameter is called thickness. And then also there's an option for thickening on both sides. So basically it goes half the distance up and half the distance down. So let's go ahead and create that. So thickness, let's spell that correctly. Thickness is equal to 0.4. Both sides is equal to false. And let's go ahead and show the result. Jupyter Lab. And there is that star thickened into a prismatic shape. Thank you for watching this video, and I will see you in the next one.